Okay, so this is the first lecture of the course. It's going to be an overview of what we're going to cover for the rest of the semester and some basics about the chemistry of the atoms that are involved with the basic molecules of life. So the basics of this course is that what we're going to be looking at is the atoms and molecules associated with life or living things. There'll be four main giant molecules and basically 4 or 5 main atoms. And that's it. Okay, it's a pretty small population sample of molecules. But with these small amounts, they can create huge variety. Some background. There's going to be absolutely no math in this class, no balancing, no moles. I'll talk a little bit about moles just because of comparison of size of molecules, but you don't have to figure anything out. There'll be no ionic compounds and very few chemical reactions. Okay, maybe 10 at the most. I'll be very specific about them. Yes, what we will be covering is covalent molecules. Again, if you don't remember what a covalent molecule is, it's a molecule, and we have to go over that definition, but it's a molecule composed mostly of non-metals and or hydrogens. We'll talk about structure, and that's really important. So we're going to talk about bonding structure, and which leads to its shape of the molecules as well. So we'll talk about how the molecules themselves, their bondings and their shapes. Electronegativity is important, and polarity, and we'll get to that probably in around when we get to lipids. And the key thing, as I said in the intro PowerPoint, is that if you know structure, you probably can figure out what the function is. And that relates now. Okay, the atoms of life, CHON and ions. Okay, CHON. CHON is carbon, hydrogen, oxygen, and nitrogen. And ions. So let's get into that. All right, there's 4 main elements that we'll be talking about. They're non-metals. They're found in the upper right-hand corner of the periodic table. These tend to have high electronegativities, and we're not going to go over. We'll go over that more in depth again when we get near lipids. And they have covalent bonds. That means they share valence electrons. The 4 main elements are carbon, nitrogen, oxygen, and hydrogen. Phosphorus and sulfur are somewhat abundant, especially in proteins and nucleic acid. And yeah, wow, that's it? Yep, that's it. Pretty small collection of atoms. So if you take 110, you learn all about all kinds of things, and it boils down just to the main guys. All right, so we're going to do a quick review of atomic structure so we can get to where we want and talk about molecules. So quick review, and I don't know how much you'll be able to remember this, but I'll let you know exactly what you need to know for the test. And right now, this is just sort of background to lead you to what you'll need to know for the first test. All right, if you remember in Chem 110 or your intro class, that carbon has 6 protons. You can find that out by looking at the atomic number. The atomic number is the number of protons. And usually an atom has, if it's all by itself, it will have the same number of electrons as it does protons. So carbon has 6 electrons. And we have a special way of figuring out how the electrons are situated around the atoms. And when we draw it out in your basic chemistry class, it kind of looked like a planetary model. But that's really not a great way of describing it. We another way to use it is use something called orbital energy diagram, and that's what I have here. And each one of these, so we have layers. So this is level 1, this is level 2, then it'll be level 3, level 4, and so forth. And all six electrons will fit carbons in the first 2 levels. Level 1 has only has 1. So each level has a certain amount of squares, and these are called orbitals. So first energy level has 1 square, and a second energy level has 4 squares. Third energy level has 9 squares. All right, kind of figure that out. The number of squares is equal to the energy level squared. You won't have to know that. Just kind of, it's just an interesting thing here. So in your general chem class, your intro class, you learned that the first 2 electrons go in the first orbital, next 2 go into this square, and then the next 2 go into this, into what we call the p subshell. So what we're interested in is not really how all these go in there, but the electrons that are in the outer energy level, because these electrons will be the electrons that interact with all other atoms. So and this outer shell is called the valence shell. And how many electrons an atom has in the outer shell these are called the valence electrons. So carbon has 6 overall electrons, but 4 of them are in the valence electrons. So those are the key electrons for carbon, and those are the electrons that will form covalent bonds with other atoms. Okay, so again, we'll just go over this. Carbon has 2 shells, and there are 4 valence electrons in the valence shell. The valence electrons are on the outside, therefore electrons that interact with the rest of the world or other atoms, and they're the bonding electrons. Okay, we had another way of showing how the electrons can go around the atom, and that's called Lewis dot structure. And the Lewis dot structure only will refer to those electrons that interact with the outside world or the valence electrons. And this is the Lewis dot structure for carbon. So remember, carbon has 4 valence electrons. 2 of them, the other 2 are buried, okay? But these 4 here are the electrons who will bond with other electrons of other atoms. Okay, covalent bonding. Okay, whenever an atom will bond to another atom, what it will do is it will decrease the potential energy, which is a good thing. There are 2 types of bonding that you should have learned about. One is ionic, and this is when you have a positively charged ion, or metal usually, interacts with a negatively charged electrical nonmetal. And the positive ion will interact with the negative ion. Positive ions are called cations, negative ions are called anions. And that attraction is called the ionic bond. And then there were covalent bonds, and covalent bonds are between nonmetals. Okay, and these are where the atoms will share unpaired electrons. Now, one of the things I want to make sure you understand is that we use the word bond to represent the interaction between atoms in a molecule. Okay, and so you have atoms and you have molecules. Molecules are made out of atoms. A molecule is 2 or more atoms that are chemically combined to form a molecule. Okay, and a specific ratio of those atoms. So water has 2 hydrogens and 1 oxygen, and they're chemically combined. All right, so again, what we're interested in is carbon, nitrogen, oxygen, and hydrogen. And here's the Lewis dot structures for each one of them. Now we won't go over to how we figure these out, but one way you can quickly figure them out is if you go to the periodic table and you see what column in there. Carbon's found in carbon row 14. Notice it has 4 valence electrons. Nitrogen is column 15. Notice it has 5 electrons. Oxygen is found in 16 and it has 6 valence electrons. Hydrogen is actually, you can put it in the 17th column, and then 17th columns have will have well, I guess we can leave hydrogen out here. It's found in the first column. That's what I mean. All right. So so carbon has 4 unpaired electrons. Each orange one is unpaired. And nitrogen has 3 unpaired. And there's 1 paired. Okay, this pair here is called a lone pair. So carbon has 4 unpaired and no lone pairs. Nitrogen has 3 unpaired and 1 unpaired lone pair. Nitrogen has 2 unpaired and 2 lone pairs, and hydrogen only has 1 unpaired. Now, wherever there's an unpaired, there can be a bond. So carbon can have 4 bonds, nitrogen 3, oxygen 2, hydrogen 1. Now, what's interesting is that carbon can have 4 ways of having bonds. It can have 4 single bonds where each dot will connect up with another atom. It can have two of the dots will connect to 2 different atoms, and 1 will connect, and 2 of the atoms will connect to the same, forming a double bond. And then you can have 2 double bonds and a triple bond and a single bond. So it has 4 ways it can bond. Nitrogen can have 3 bonds and it can have 3 ways to bond. Oxygen has 2 bonds and it has 2 ways it can bond, 2 single bonds and 1 double bond. And hydrogen has 1 bond and 1 way to bond. So what we want to do is whenever you see carbon, make sure it has 4 bonds. And the carbon cannot have a 4-ple bond or a quadruple bond. It's got to be one of these 4 combinations. Nitrogen will always have 3 bonds. Okay, 3 dashes and a lone pair. And oxygen always 2 dashes and 2 pairs, and hydrogen 1 dash. Now you won't have to come up with these. You'll see how to use them for this class. So you won't have to connect dots like you did in Chem 110. What you just have to make sure is that whenever you see a structure with carbon, it always has 4 bonds. If you see nitrogen, it has to have 3 bonds and a lone pair. Oxygen has 2 bonds and 2 lone pairs, and hydrogen 1. Okay, and we'll go over several of these in the next lecture, especially when we start talking about the kinds of like carbohydrates and lipids and so forth. We'll be drawing out their bonding structures. Again, whenever you see carbon, you'll see it has 4 bonds, and hydrogen 1 bond, etc. Okay, when we draw these structures out, we draw them out on the board or on a piece of paper or on PowerPoint here, and they're all on flat structures. On a flat surface. So what we want to make sure, but that's not really how they are in nature. Okay, in nature, the molecules are not flat; they extend into 3 dimensions. So what we're going to do now is we're going to see how these guys look in 3 dimensions. Okay, now to figure out the 3-dimensional shapes of molecules, what we use is a theory called the valence shell electron pair repulsion. Now, in my classes, I like to demonstrate this in a way that you can see using models, and actually I will sort of pretend to be a molecule myself, but it's kind of hard to show you here. Maybe if I get time, maybe I'll go in and show you on another PowerPoint on this, or a slide. So what I'm going to do is I'm just going to cut to the chase to show you the different shapes of molecules, and hopefully you'll be able to visualize them a little bit. Okay, so what we want to do is go over the basic shapes that molecules have, and how we can determine the shapes and how we can visualize them. All right, so we have 5 different shapes here, and every one of these have two main components. They have center atoms, and then they have atoms attached to that center atom. The first shape is a center atom with 2 atoms attached. Okay, now the second one is center atom with 3 atoms attached, and this one has center atom with 4. This is the atom with molecule with 3 attached, similar to this one over here, but this one has a lone pair attached to it, and that's going to change the shape. And then you have this one out here has a center atom, 2 atoms attached, just like this guy over here, but it has lone pair, and that changes the shape compared to this one. Okay, so let's go over these shapes and maybe how you can kind of visualize them. All right, this first shape here, it kind of looks like a bar. Okay, so if you have a stretched out, like if you had an iron bar, and it's stretched out like straight out, so it straight out like a line. So that this shape is called a linear molecule, linear shape. How you can tell if you're given the bonding structure like this right here, how you can tell that this is linear is it has the center atom has 2 atoms attached to it, and it doesn't matter the number of bonds. Okay, now I know it has 4 bonds, but it only has 2 attachments, and there's no lone pairs on the center atom. So there's 2 attachments, no lone pairs. That will give you a linear molecule. In the second type of molecule, this kind of looks like a Y or a triangle, a flat triangle. So all the atoms in this shape here are all, if you were laid them down on the table, all 4 of these atoms would lie on the table. Okay, and they form a triangle shape. So the name of this molecule, shape of molecule, is triangular, or trigonal, because it has a triangle shape, and because it's flat and lay on the table, we call it trigonal planar. Now the way to tell if you have a trigonal planar molecule is that if the center atom has 3 atoms attached, okay, and no lone pairs. Okay, and here's an example. So if you had carbon, it has carbon. So there's a double bond here, but this guy still only has 3. This carbon has 3 attachments, no lone pairs. So if you notice, the carbon, this first one, carbon had 4 bonds and 2 attachments. This one had, carbon here also has 4 bonds, but it only has 3 attachments. Okay, so the next one, the center atom, and it doesn't have to be carbon, it could be any atom here. So the center atom now has 4 different things attached to it. Now this one is kind of hard to visualize. So one way to think about it is that these three atoms down here, that's where I'm pointing to, are sitting on a table, and this guy here kind of sits above it. So it's like a tripod. Okay, so it's a tripod with an extra atom sticking out the top. So you have a tripod shape with an extra atom coming out of the top. Now, this shape here in geometry is given the name tetrahedron, and we call that tetrahedral. So if you see a molecule that has center atom has 4 attachment, it's tetrahedral. All right, and usually what we're going to see is that this is quite prevalent in all the atoms all the molecules that we see. This is probably the most prevalent shape in all of the molecules in life. Okay, and the next one, you have the center atom with 3 atoms attached. Okay, similar to this guy over here. Okay, so this one also forms a triangle. The 3 atoms out here form a triangle, but the center atom doesn't sit on the table like this guy over here. It sits above the table, and that's because of this lone pair up here that you can think it kind of pulls this atom up off the table. And so it has a trigonal shape, just like this guy, because it kind of forms this Y shape or triangle shape. But it's not all the atoms aren't in the same plane anymore. Okay, this shape kind of looks like this guy without this atom here. So this shape here of the 4 atoms is called trigonal pyramidal. Now the shape doesn't include the lone pair. So the shape is just this shape here. So it's these 3 guys and this guy above it. Okay, so it's just like this model here, but this atom is sitting above it. All right, and finally the last one is where you have the center atom with 2 atoms attached, just like the first one. But what happens is the center atom has 2 lone pairs on it, and those 2 lone pairs pull that guy up. So like over here in the linear, it'd be like pulling this guy up, and it's no longer straight across. Okay, and so that shape is bent. Okay, so these lone pairs bend the molecule. Right, one way that you can tell if you have this shape here is if you have an atom with 2 things attached, 2 atoms attached, and 2 lone pairs. Okay, so let's go over an example of what I expect you to know about it. So on a test, what I'll probably do is I'll give you a model like a molecule like this, and so let's go over the atoms first and see if everything is okay with the number that each atom has the right number of bonds and lone pairs. So nitrogen should have has 3 bonds and 1 lone pair, so that's good. That's what it's supposed to have. Each carbon should have 4 bonds. This one has 4. This carbon has 4 bonds. 1, 2, 3, 4. Oxygen should have 2 bonds and 2 lone pairs. There's 2 bonds, 2 lone pairs, 2 bonds, 2 lone pairs, and hydrogen 1 bond. Okay. Now, what we want to do is figure out the shapes around each one of the center atoms. So a center atom is a inside atom of a molecule. So this hydrogen is not a center atom because it's on the outside. This is not a center atom. So I've circled the center atoms, and what we're going to do is go over, try to figure out the shapes of each one of around each one of these atoms. So this is one molecule, and we'll see that this molecule is called an amino acid. We get the proteins. The molecule can have more than one shape in it. In this molecule here can have 4 different shapes in it, because it has 4 different center atoms. So on the test, what I'll do is draw something, a molecule out like this and circle, and you'll have to do what I'm going to do right now. So let's look at the first this first atom here. So nitrogen should have, nitrogen, this nitrogen has 3 connections, 1, 2, 3, and 1 lone pair. So it's going to be trigonal, because it has 3 connections. Now it can either be planar or pyramidal. If it has no lone pairs, then it's planar, and if it has lone pairs on the center atoms, then it's pyramidal. And you can see that this nitrogen has 3 connections, 1, 2, 3, and a lone pair. So this is trigonal pyramidal. So trigonal pyramidal. Right, now let's just go to this carbon here. This carbon here has 4 connections, 1, 2, 3, 4. Okay, any atom, center atom that has 4 connections has a tetrahedral shape. Okay. All right, this carbon here has 3 connections and no lone pairs, so this is going to be trigonal planar. Okay, which is different than this guy out here. This is trigonal because it has 3 connections, but this has no lone pairs, so it's planar, trigonal planar. And then finally, this guy out here, this oxygen has 2 connections. Okay, so it can be either linear or bent. If it had no lone pairs, it'd be linear, but it does have lone pairs, so this is bent. Okay, so basically what you have to know from what I've talked about up to now is the number of bonds and lone pairs that carbon, nitrogen, oxygen, and hydrogen have, and the 5 different shapes, and how to determine by looking at the bonding structure, what is the shape of that molecule. Okay, or shape in a molecule. So now what we're going to do is we're going to preview the molecules that we're going to be talking about for the rest of the semester. And these are the molecules of life. Okay, so okay. All right, so what we're going to be studying is biological macromolecules, the BMMs. Okay, biological means life, macro means big. So what we're going to be studying is life's big molecules. Again, what molecules are combinations of atoms, chemically combined. Right. So these are molecules combined with thousands and thousands of atoms. Okay. There are 4 different types of macromolecules. There's going to be carbohydrates, which include sugars, lipids, which include fats and steroids, proteins, and nucleic acids, which are DNA and RNA. Let me just give you a brief overview about how big these molecules are, because I think it's important to understand that the immensity and size of these molecules and how big they are compared to the kinds of molecules that you might have learned about in 110. I talked about in the intro PowerPoint in the syllabus that the molecules that you see in 110 tend to be really, really small compared to the molecules that we will see here. So the biggest molecule you probably studied in chemistry, even though you may not remember it, might have been calcium phosphate. And calcium phosphate, here's the chemical formula. So it's 3 calciums and 2 phosphates. Okay, and it's a fairly big molecule, right? Now what we want to do is we're going to use the molar mass, and you don't have to you don't have to figure this out, but this is a way to sort of understand how big this molecule is. So this molecule is 310 grams for its molar mass. So if you have a mole of this, and again, you don't have to know what a mole is, it's this quantity of particles, but that quantity is going to weigh 310 grams. Now water, on the other hand, weighs 18 grams per mole. So if you have 1 mole of water, it weighs 18 grams. And if you have 1 mole of calcium phosphate, it weighs 310. So they have the same quantities, but they weigh much different according to how big they are. Okay, so calcium phosphate is between 15 to 20 times bigger than water. All right. So it's pretty big. So calcium phosphate is a pretty big molecule. We'll just say it's 15 times bigger. So if you had 15 waters, that'd be the size of just one of these guys right here. Okay. So that's kind of where you can kind of visualize it. It takes 15 waters to take up the same space as these guys. All right. All right, so let's talk a little bit about the size of molecules that we're going to talk about in this class. So starch, on average, is about 750 grams. So compared to water, this would be about 40 times bigger than water. Okay. Fatty acid, okay, again, about 40 to 50 times bigger than water. And then you got hemoglobin, which is a protein. It's 65,000 grams per mole, which is about 3,500 times bigger than water. Okay, so it's like hemoglobin's like the size of 3,500 water molecules. And finally, the size of the gene that will code for a hemoglobin. So this is DNA. The DNA that will help make hemoglobin is 300,000 grams per mole, which is about 17,000 water molecules. Okay, so if you think about it, these molecules are huge. Now, the biggest molecule in the biggest protein, biological molecule in the world is something called titin. And if you were to compare titin to water, it's like comparing a house to two of the largest buildings in the world, the Burj Khalifas in Dubai. Okay, each one of these is a quarter mile. So if you stack these guys on top of each other, they'd be a half mile high. Well, if you compare a house to a half mile high building, is like comparing water to titan. That's how big this molecule is compared to water. So this is just to give you an idea of the size of the molecules that we're going to be talking about, especially proteins and nucleic acids are going to be humongous. Okay, I said this is the biggest molecule. This is the biggest protein. Okay, there's bigger molecules. In fact, DNA, the DNA that makes this proteins is actually 3 times bigger than this guy. So that's like a mile and a half of buildings. Okay, so these compared to a house. So these molecules that we're going to be talking about are huge. Now, how does nature make these gigantic molecules? And they have to make them relatively easy because it can't be a complex method to come up with these molecules. And the way I talked about this in the first PowerPoint is the way that nature does this is it uses building blocks to build these enormous buildings. So just like you wouldn't, like I said in the previous PowerPoint, you wouldn't pretty much, if you build a house, you're just not going to pour a giant block of cement and live it. Now you might, okay, but it's not very efficient. What you're going to do is you're going to get building blocks, you're going to get bricks, and you're going to build your bricks. You're going to get steel bars and frames and so forth to build those buildings. And so these giant molecules will have building blocks and mortar, the bonds. And here are the 4 different molecules, and here's 4 different examples. Okay, so an example of a carbohydrate, one of the giant carbohydrate molecules is starch, and the building blocks for the starch are glucose. And the mortar, okay, is called a glycosidic bond. All right, example of a lipid is a triglyceride. Okay, so that's the big molecule. And the parts, the molecules, the building blocks of that are fatty acids. And the mortars are esters. For proteins, the building blocks are amino acids. And for nucleic acids, the building blocks are nucleotides. Now for the test, what you're going to have to know is this column here, the macromolecules and their associated building blocks. We will go over these individually when we get to each one of these different molecules. Okay, so you don't have to know the examples or the bonds. You just have to know the macromolecules and their building blocks. So here's an example of each one of them. So this is a starch molecule. Okay, and every one of these little guys here is a glucose molecule. So that's a building block, and each one of these glucoses are held together by a glycosidic bond. So you can see that this molecule is a very big molecule, and what makes it big is that it has several hundred glucose molecules attached. All right, a triglyceride is a bit smaller, quite a bit smaller, but it has a general idea. It has, so this molecule here is called a triglyceride. It's a lipid, and the building blocks are the fatty acids. Okay, and what holds these together are the ester bonds. Okay. Okay, for proteins. So this protein is hemoglobin. It's a protein. It's not. There's thousands of different proteins, but here you can see the red and the blue, the greens. These all are amino acids. Okay, so this giant molecule here is made of a building block called amino acids, and amino acids are held together by something called a bond called the peptide bond. And then you have nucleic acids like DNA. Now it's hard to see it here, but these on each one of these, you see this line here, okay, where I have my pointer. That's a nucleotide. And then there's another nucleotide, another nucleotide, another nucleotide, nucleotide, nucleotide. So wherever you see a line going across, that's a nucleotide. So this DNA is made out of several hundred, maybe thousands of these nucleotides. So these are building blocks, and each one of the nucleotides held together by a phosphodiester bond. Okay, now another key thing here, I told you, is in the first PowerPoint I said there are 2 main things about that I'll keep on coming back, themes, common themes that I'll keep coming back to. One is building blocks will make these giant molecules, and the other is that structure makes function. Okay, in fact, this is more than just macromolecules. It's everything in nature. Everything in nature is guided by a simple tenet, and that structure determines function. So something's structure is going to determine how it functions. So if you see these 2 cars here, you got your Bugatti and you got your semi, okay? Which one is quicker? Okay, you don't really have to even think about it, okay? Well, you can see that this guy's littler, and you could probably think that it moves faster, and if you know anything about it, you know that it can move fast. And this guy here can carry more weight, and that's because it's giant and it has a giant place to put a trailer. Okay, so its structure determines what it can do. And this is common throughout nature as well, and that includes our macromolecules. So our macromolecules, what we're going to do is we'll look at the shapes of the building blocks, their structures, see, and relate to that how how those building blocks function, what's their jobs because of their structure, and then when we combine those guys together to form the giant molecules, what are these giant molecules structure and how does that structure relate to how they function? All right, here's another example of structure function. Here's a tree, okay? Why does a tree have its particular shape? Okay, so a tree has all these leaves, and the leaves form this giant canopy, and there's lots and lots of leaves. And what the purpose of all these leaves is to capture sunlight. Okay, and capture sunlight and carbon dioxide. So each one of these leaves, so the more leaves you have, the more you're going to catch carbon dioxide, but also you want to have them exposed to sunlight. And so the giant canopy here gives more opportunity to catch carbon dioxide and also capture sunlight. Okay, the root system. The root system spreads out, and what it does is it spreads out to find water. Okay, and each tree has its own root system. This root system, which spreads out horizontally and not so much vertically. Okay, and what it does is it reaches out as far as it can to find water. So the structure of a tree determines how it's going to grow and how it's going to live. Okay, so for each macromolecule, we will look at the structure and function of the building blocks, and then we'll combine them with bonds, and then we'll look at the structure of the macromolecules and therefore its function. So structure, function. We'll see this in carbohydrates, lipids, proteins, and nucleic acids. Okay, the next PowerPoint we'll get into the starting point of the macromolecules, which will relate which will be hydrocarbons.